Um, However, these conditions are a bit restrictive, and real life problems or the general nonlinear problems may not satisfy these assumptions, especially this assumption about being close to x star. We don't really know x star, so how can we choose an initial point which is close to x star? Okay. So there are some ways around each of these difficulties, and we will discuss them now. So let's say what happens when gk is positive definite, but we are not very close to x star. Okay, so if g's are positive definite, but we are not close enough to x star, then we may not actually converge. We may oscillate between two or more points and never reach x star. Okay, and again the book has a nice example of a fourth order polynomial, a very simple function in two variables, which converges extremely fast if we start very close to x star, but doesn't converge if we are a little bit far away. So so this is a big problem. If in fact what may happen is that the function value may not even decrease if we take a Newton step, right? So this delta star is called the Newton step, and this may not even lead to a decrease in the function value. So there are some ways around this difficulty, and the book has nice suggestions on these ways. So if gk is positive definite, but delta star or delta k is a poor step, that means my function is not decreasing, then we can do a line search. Along which line? Along delta. May be good or useful. Okay, and this we know is a direction of descent. We just discussed this about 5 minutes back, that if gk is positive definite, then this is a direction of descent. But if I just take delta k step, then I it may not lead to a decrease in f. So then I might do a line search around this point and get a point where I see some improvement. If gk is not positive definite, then there are bigger problems. Then the direction of delta k may not be or maybe an ascent direction. And we may not want to go there. In fact, we can do line search in the negative of this direction. But if we resort to these methods, and even the third trick that we will shortly discuss, is we lose quadratic convergence. Okay, so all these modifications lead to a slowdown of the method, at least theoretically speaking, but practically we will have to do it because otherwise the method may not even converge. It may also happen that neither delta k nor minus of delta k is a descent direction. That means none of them are ascent directions, none of them are descent directions, which means that it is perpendicular to the gradient. So that means gk delta k transpose is actually 0. That means the function is flat along this direction. Then it's not even clear whether we should do any line search along delta k or not. In this case, we might have to modify the direction. This modification of the direction may also be required in the above 2 points. Even though I may have a descent direction, it may not be a great descent direction, so I might want to search in a slightly different direction. So one way of modifying the direction and doing a line search is to just perturb this this direction by a small amount. So a different direction for line search so remember that Newton's method is fast, so we would like to use a direction suggested by Newton, but we also want to make sure it's a descent direction. So instead of having a solution to the system gk delta k equal to minus of small gk, I change it to gk plus mu times I sk equal to minus gk, and then do a line search along sk. So mu is a scalar and greater than 0, chosen in such a way so that this whole thing becomes positive definite. So if certain eigenvalues of gk are less than 0, then I can add some diagonal entries. So this is a diagonal matrix with some positive entries, so that this whole thing becomes positive definite, and this is always possible. From linear algebra we know this. So we don't want mu to be too big. If it is too big, then I am very close to the steepest descent, which I know is slow. But if mu is too small, then this whole thing may not be positive definite, and then I may have problems mentioned earlier. So we would like a sufficiently small mu so that this whole thing becomes positive definite. So this is called some correction of the step length or the step direction, and we will try to look at these methods a little bit later in the next chapters. Let's mention a few more difficulties with Newton's method. So first is we need the Hessian matrix, okay, which might be big. For example, if n is 1000, then gk has million elements, okay, and n equal to 1000 is not too big by today's standards. The solvers are capable of solving for much bigger n, especially when these g's are sparse, okay. So we really want this g to be sparse, okay. If this is dense, then we will have to store so many elements, and we will run out of computer memory, okay. Must be sparse. And we must have good routines to estimate, good routines to compute g. So either the user has to specify what g is, and have a function written which generates these second order derivatives. If we are relying on numerical approximation schemes to compute derivatives, then we have to be careful about the perturbation that we want from the current point to evaluate these gradients and Hessians. The second difficulty is that once we have gradients and Hessians, I need to solve this system of equations. So again, if I have n variables, then it takes order n cube, so roughly some constant times n cube steps to solve a system of equations in n variables. Okay, to solve a system, linear system. So if you have a system Ax equal to b, then typically the number of steps required to solve Ax equal to b is roughly of the order of n cube. So this might become expensive, especially when n is large, and lead to some slowdown. We never solved such a system of equations in the steepest descent algorithm. So there each step of the algorithm was quite cheap, but the analysis shows that the number of iterations would be too large in steepest descent, even though each iteration is relatively quick. Newton's method may take fewer iterations if I am close to the solution, but each iteration may take a longer time. So this really makes the Newton's method not very practical for general purpose unconstrained optimization. So we will look at some methods which try to overcome these difficulties of the Newton's method. More specifically, we will look at methods called quasi-Newton methods. So these methods try to overcome both theoretical and computational difficulties of Newton's method. This is not one method. There are many variants of these methods, but as a group or a family, these are together called quasi-Newton methods or quasi-Newton methods. Two very important methods are DFP and DFGS, and these methods are very practical and very much in use, especially BFGS. So the improvements these methods propose are, number one, do not evaluate the Hessian of the function. Instead, estimate it from gradients. Especially the gradients that we used in the previous iterations. So looking at difference of these gradients, I can get a rough estimate of the Hessian. And second, it is just a small addition to the first one, is you don't evaluate this estimated Hessian. Small updates to the Hessian in every iteration, or its inverse in every iteration. So we don't do expensive steps in every iteration, and we don't even solve this system of equations in some of these methods. So avoid solving the system of equations. So the time spent in every iteration goes to order n square from n cube earlier. Okay. We still have to do line search. So we can rely on the methods of line search from the previous chapter. And we still need to do these order n square operations, which are primarily products of a matrix and a vector. And this really improves the whole method a lot, but the downside is that we lose quadratic convergence. So my method becomes correct, which is of my primary concern, that it should not fail ever. So to make it more robust and to do these failures and to make it computationally more efficient, we allow many approximations, and in process we sacrifice some speed, but we gain a lot in terms of the number of problems that can now be solved, and also in terms of speed as compared to steepest descent. So with that remark, we will stop here and continue with this DFP and BFGS in our next lecture.